Look up at the night sky. What do you see? Pinpricks of light, distant suns, a vastness beyond comprehension. Our journey begins right here, on our pale blue dot, as we set out to explore the cosmos. From the dawn of humanity, we've gazed at the stars, asking questions, seeking answers in the celestial dance above. The universe is more than just a collection of objects. It's a story. A story written in the language of physics and chemistry, a story of birth, death, and constant transformation. Our first destination is our cosmic backyard, the solar system. At its heart, a fiery giant, the Sun holds court, its immense gravity binding a diverse collection of planets in its sway. Orbiting the Sun are 8 planets, each a world unto itself. From the scorching hellscape of Venus to the icy plains of Mars, each planet tells a tale of cosmic evolution. Moons too hold their own allure, like Io, spewing lava into the cold vacuum of space, and Europa, its icy surface potentially harboring a hidden ocean. As we leave our solar system behind, we begin to grasp the true scale of the universe. The distances are staggering, measured not in miles or kilometers, but in light years. The distance light travels in a year. Even our closest stellar neighbor, Proxima Centauri, is over 4 light-years away. When we look at the stars, we are peering back in time, witnessing light that began its journey long ago. Beyond the stars lie galaxies, vast islands of billions, even trillions of stars, each a swirling cosmic metropolis. Our first stop takes us to Mercury, the smallest planet in our solar system and the closest to the Sun. This proximity makes Mercury a world of extremes, with temperatures soaring to 800 degrees Fahrenheit during the day and plummeting to negative 290 degrees at night. Despite its harsh conditions, Mercury is a fascinating world, its surface heavily cratered, a testament to countless impacts over billions of years. One of Mercury's most intriguing features is its slow rotation, taking 59 Earth days to complete one rotation on its axis. This means that a single day on Mercury is longer than its entire year. Next, we journey to Venus, often called Earth's twin due to its similar size and mass. But Venus is a world of scorching heat, crushing pressure, and a toxic atmosphere, shrouded in thick clouds of sulfuric acid. The surface of Venus is a desolate wasteland, hidden from our view by dense, swirling clouds that trap heat, creating a runaway greenhouse effect. This extreme heat makes Venus the hottest planet in our solar system, even hotter than Mercury. Despite its hostile environment, Venus holds clues to the early evolution of our own planet. Our journey continues to Mars, the red planet, a world that has captivated humanity for centuries. Mars is a cold, dry desert world, its surface sculpted by ancient volcanoes, vast canyons, and evidence of past liquid water. While Mars today is a frigid desert, evidence suggests that billions of years ago, it may have been a warmer, wetter world, perhaps even harboring life. One of Mars's most striking features is Olympus Mons, the largest volcano in our solar system, towering over 13 miles high. Mars also boasts Valles Marineris, a vast canyon system that stretches over 2,500 miles, dwarfing the Grand Canyon on Earth. Our next destination takes us to Jupiter, the largest planet in our solar system, a gas giant so immense that it could hold over 1,300 Earths within its swirling clouds. Jupiter's most recognizable feature is the Great Red Spot, a massive storm system larger than Earth that has been raging for at least 400 years. Jupiter is not just a giant planet, it's also a mini solar system, orbited by over 79 known moons. Among these moons, 4 stand out: Io, Europa, Ganymede, and Callisto, known as the Galilean moons. Europa, covered in a smooth icy shell, may conceal a vast salty ocean beneath, potentially harboring life. Our journey through the solar system takes us next to Saturn, the Ringed Wonder, a gas giant renowned for its stunning system of rings that stretch over 175,000 miles across. These rings, composed of countless particles of ice and rock, are a celestial ballet, a testament to the beauty and wonder of our universe. Saturn's rings are not solid structures, but are made up of billions of individual particles, ranging in size from tiny grains of dust to chunks of ice as large as houses. Saturn, like Jupiter, is a gas giant, composed primarily of hydrogen and helium. Titan, Saturn's largest moon, is larger than the planet Mercury and is shrouded in a dense atmosphere, making it the only moon in our solar system known to have a substantial atmosphere. As we leave behind the familiar planets of our solar system, we venture into the vast expanse beyond, a realm dominated by stars, the building blocks of galaxies and the celestial lighthouses that have guided humanity for millennia. Stars, unlike planets, are not content to simply orbit a larger body. They are self-luminous, generating their own energy through the process of nuclear fusion. This fusion occurs deep within the core of a star, where temperatures and pressures are so extreme that atoms of hydrogen are forced together, fusing into helium and releasing an immense amount of energy. This energy, in the form of light and heat, radiates outward from the star's core, eventually escaping into space and traveling across vast distances before reaching our eyes. Understanding the life cycle of stars is key to unraveling the mysteries of the universe, from the formation of galaxies to the creation of the elements that make up our very bodies. The story of a star's life begins in the cold, dark depths of space within vast clouds of gas and dust known as nebulae. These nebulae, often remnants of previous generations of stars, serve as stellar nurseries, providing the raw materials and conditions necessary for new stars to form. Within these nebulae, gravity is the architect, slowly drawing together clumps of gas and dust, pulling them closer and closer together. As these clumps grow larger, their gravitational pull intensifies, attracting even more material and causing them to collapse in on themselves. Eventually, the core becomes so hot and dense that nuclear fusion ignites, marking the birth of a star. The life cycle of stars, from hydrogen to heavy elements. Once a star ignites nuclear fusion in its core, it enters the main sequence, a long period of stability during which it fuses hydrogen into helium, releasing a steady stream of energy. The length of time a star spends on the main sequence depends on its mass, with more massive stars burning through their fuel much faster than their smaller counterparts. Massive stars may only spend a few million years on the main sequence before exhausting their hydrogen fuel and evolving into red giants. Smaller stars like our Sun are much more frugal with their fuel, spending billions of years on the main sequence. Constellations, connecting the cosmic dots. Since time immemorial, humans have gazed up at the stars, seeking patterns and meaning in the celestial tapestry overhead. These patterns, known as constellations, are not actual groupings of stars, but rather chance alignments of stars that lie at vastly different distances from Earth. The constellations we recognize today have their roots in ancient cultures, with many of their names and stories originating from Greek, Roman, and Babylonian mythology. The same stars that inspired ancient civilizations to create myths and legends continue to captivate us today, reminding us of our shared human experience and our enduring fascination with the cosmos. Binary and multiple star systems, stellar choreography. While our Sun is a solitary star, many stars in the Milky Way exist in binary or multiple star systems, locked in a delicate gravitational dance with one or more companion stars. These stellar partnerships can take many forms, from close binaries where the stars are nearly touching to wide binaries separated by vast distances, their gravitational bond keeping them tethered together despite the gulf of space between them. Binary stars are not merely curiosities, they provide astronomers with valuable insights into the properties of stars. By observing the orbital motions of binary stars, astronomers can determine the masses of the stars, a crucial parameter for understanding stellar evolution. Multiple star systems with 3 or more stars can exhibit even more complex and dynamic interactions. These systems often involve hierarchical structures, with pairs of stars orbiting each other while also orbiting a common center of mass with other stars in the system. The study of binary and multiple star systems is a testament to the power of gravity, the fundamental force that shapes the universe from the largest scales of galaxy clusters down to the interactions of individual stars. These stellar partnerships remind us that the cosmos is a dynamic and ever-changing place, where even the seemingly immutable stars are engaged in a celestial ballet, their movements governed by the laws of physics. Our Sun, a seemingly ordinary yellow dwarf star, is anything but ordinary. It is the center of our solar system, the source of our light and warmth, and the engine that drives our planet's climate and weather patterns. While the Sun may be just one of billions of stars in the Milky Way, it holds a unique significance for us, for it is the star that makes life on Earth possible. The Sun is a massive ball of hot, glowing gas, primarily hydrogen and helium, held together by its own gravity. Deep within its core, nuclear fusion reactions convert hydrogen into helium, releasing an immense amount of energy that radiates outward, providing the light and heat that sustain life on Earth. While the Sun may seem unchanging from our perspective on Earth, it is a dynamic and active star. Its surface is constantly churning with activity, with sunspots, solar flares, and coronal mass ejections releasing bursts of energy and charged particles into space. These solar events can have a profound impact on Earth, disrupting communications, causing auroras, and even posing a threat to satellites and power grids. Despite its occasional outbursts, the Sun has been a remarkably stable star for billions of years, providing a consistent source of energy that has allowed life to evolve and flourish on Earth. As we continue to explore the cosmos and search for signs of life beyond our planet, we do so with a deep appreciation for the extraordinary star that makes our own existence possible. As we venture further out into the cosmos, beyond the familiar constellations and the scattered stars of our Milky Way, we encounter vast islands of stars, each a swirling metropolis of billions, even trillions of suns. These are galaxies, the fundamental building blocks of the universe. For centuries, these faint patches of light remained enigmatic, their true nature hidden from view. It wasn't until the early 20th century that astronomers, armed with increasingly powerful telescopes, began to unravel the true nature of galaxies. This realization revolutionized our understanding of the universe, expanding its scale from the familiar confines of the Milky Way to a cosmos teeming with countless galaxies. Our journey begins at home, within the Milky Way, a barred spiral galaxy housing our Sun and billions of stars. From our vantage point, we see a faint band of light stretching across the night sky. At its center lies a supermassive black hole, binding the galaxy together. Surrounding it is a central bulge of older stars, with spiral arms traced by young, hot stars. Our solar system resides in a quiet corner, about 26,000 light-years from the center. We complete one orbit around the galactic center every 230 million years. As we venture beyond the Milky Way, we encounter a dazzling array of galactic shapes and sizes, a cosmic zoo of stellar metropolises, each sculpted by its own unique history of star formation, galactic collisions, and the influence of dark matter. This diversity provides clues to galaxy formation and evolution, revealing the interplay of gravity, gas dynamics, and stellar feedback. Spiral galaxies, like our own Milky Way and Andromeda, are characterized by their graceful spiral arms, regions of active star formation. Elliptical galaxies appear smooth and featureless, lacking the spiral arms of their spiral counterparts. These galaxies are thought to be the products of galactic mergers, where 2 or more spiral galaxies collide. Their stars scatter into a more spheroidal distribution. In addition to spirals and ellipticals, astronomers have identified irregular galaxies, their shapes defying easy classification. These galaxies often exhibit peculiar morphologies, the result of gravitational interactions with neighboring galaxies. The study of galaxy morphology is like piecing together a cosmic puzzle, each galaxy's shape offering clues to its past. By classifying and analyzing galaxies, astronomers aim to unravel the secrets of galaxy formation and evolution, shedding light on the grand cosmic dance that has shaped the universe. While most galaxies emit a relatively steady stream of light from their stars, a small percentage shine with an extraordinary brilliance, their cores blazing with the energy of 1 trillion suns. These are active galaxies, powered by supermassive black holes lurking at their centers, their immense gravitational pull drawing in surrounding gas and dust, unleashing a torrent of energy as matter spirals inward toward the event horizon. As in falling material swirls around the black hole, it forms an accretion disk, a superheated disk of gas and dust that can outshine the combined light of billions of stars. This intense radiation, emitted across the electromagnetic spectrum, from radio waves to X-rays, can be detected billions of light years away, making active galaxies some of the most distant objects visible to astronomers. Among the most luminous and energetic active galaxies are quasars, thought to be powered by supermassive black holes feasting on an abundant supply of gas and dust in the early universe. These distant beacons shine with the light of 100 galaxies, compressed into a region no larger than our solar system. The study of active galaxies provides a unique window into the extreme physics at play in the vicinity of supermassive black holes. By observing the radiation emitted from these cosmic powerhouses, astronomers can probe the properties of black holes, test the limits of Einstein's theory of general relativity, and gain a deeper understanding of the role black holes play in the evolution of galaxies. In the vast expanse of space, galaxies are dynamic entities engaged in a cosmic dance of gravity and motion. Galaxies can interact and collide, triggering bursts of star formation and reshaping their destinies. Collisions can be violent, with galaxies merging, stars scattering, and gas clouds igniting starbirth. Our Milky Way is on a collision course with the Andromeda Galaxy. In about 4 billion years, these giants will merge, distorting shapes and scattering stars. The night sky will transform, with stars of Andromeda mingling with those of the Milky Way. Our journey through the realm of galaxies culminates with a profound realization: the universe is expanding. This expansion, discovered in the 1920s by astronomer Edwin Hubble, means that the fabric of space-time itself is stretching, carrying galaxies along for the ride. As a result, distant galaxies are moving away from us, and the farther away a galaxy is, the faster it appears to be receding. This expansion has profound implications for our understanding of the universe. It suggests that the universe began from a hot, dense state, known as the Big Bang, and has been expanding and cooling ever since. The expansion also affects the light from distant galaxies, stretching its wavelength and causing it to appear redder than it would if the universe were static. This phenomenon, known as redshift, provides astronomers with a tool for measuring cosmic distances and studying the history of the universe. The expansion of the universe is a testament to the power of the Big Bang and the ongoing evolution of the cosmos. As galaxies continue to move apart, the universe will continue to cool and expand, becoming increasingly dark and diffuse over time. The fate of the universe is uncertain, but the expansion suggests that it will continue to evolve for billions, perhaps trillions of years to come. Our exploration of the universe's wonders now takes us to one of the most enigmatic phenomena: black holes. These cosmic abysses are regions of space-time where gravity is so strong that nothing, not even light, can escape. Imagine a place where the very fabric of space and time is warped beyond recognition. Black holes form when massive stars collapse under their own gravity. The core implodes, increasing density and gravitational pull, leading to a singularity. Surrounding the singularity is the event horizon, the point of no return. Once crossed, an object is drawn toward the singularity, its fate sealed by gravity. While stellar mass black holes formed from the collapse of individual stars are fascinating, astronomers have discovered even more massive black holes, millions or billions of times the mass of our Sun, at galaxy centers. These supermassive black holes influence galaxy evolution, affecting stars and gas clouds. They grow over billions of years through mergers and accreting gas and dust. Powerful jets of energy can erupt from their poles, extending for thousands of light years. These jets can trigger star formation and shape galaxy evolution. Observing their radiation helps astronomers probe black hole properties and test general relativity. Our cosmic journey now takes us to the ethereal realms of nebulae, vast clouds of gas and dust scattered throughout the Milky Way and beyond. These interstellar clouds, often illuminated by the light of nearby stars, are both stellar nurseries and graveyards, places where stars are born, live out their lives, and eventually return their material to the interstellar medium, enriching it for future generations of stars. Emission nebulae, some of the most visually stunning objects in the cosmos, glow with a vibrant palette of colors, the result of ultraviolet radiation from nearby hot young stars ionizing the surrounding gas. These nebulae are often associated with regions of active star formation, where the gas and dust are compressed, triggering the collapse of clouds and the birth of new stars. Reflection nebulae, as their name suggests, reflect the light of nearby stars. These nebulae are composed primarily of dust grains that scatter and reflect starlight, giving them a characteristic blue hue. Reflection nebulae often appear near star-forming regions, their dust clouds illuminated by the light of young, hot stars. Planetary nebulae, despite their name, have nothing to do with planets. These expanding shells of gas and dust are formed when stars like our Sun reach the end of their lives and shed their outer layers into space. The ejected material is illuminated by the dying star's hot core, creating intricate and often symmetrical patterns that resemble giant cosmic soap bubbles. As we peer deeper into the cosmos, our telescopes capture light that has traveled for billions of years, revealing a universe vastly different from the one we observe today. Among the most distant and enigmatic objects visible to astronomers are quasars, incredibly luminous and distant active galactic nuclei powered by supermassive black holes feasting on an abundant supply of gas and dust in the early universe. Quasars are thought to represent a brief but intense phase in the evolution of galaxies, a time when their central black holes were actively accreting material at prodigious rates, releasing enormous amounts of energy that could outshine the combined light of hundreds of galaxies. These cosmic beacons shine with the light of 100 galaxies, compressed into a region no larger than our solar system, making them visible across vast cosmic distances. The discovery of quasars in the 1960s revolutionized our understanding of the early universe, providing evidence that galaxies were more active and luminous in the distant past. By studying quasars, astronomers can probe the properties of supermassive black holes, investigate the conditions in the early universe, and gain insights into the processes that drove galaxy formation and evolution. As we continue to explore the distant universe, we expect to discover even more quasars, their light revealing the secrets of the early cosmos and shedding light on the era when galaxies were first forming and supermassive black holes were coming into their own. Our cosmic journey culminates with a glimpse of the universe in its infancy, a faint afterglow of the Big Bang that pervades all of space. This afterglow, known as the cosmic microwave background, CMB, is a faint whisper of radiation that originated just 380,000 years after the Big Bang, when the universe had cooled enough for protons and electrons to combine and form neutral hydrogen atoms, allowing light to travel freely for the first time. The CMB is a treasure trove of information about the early universe, carrying with it the imprint of the conditions that existed when the universe was just a fraction of its current age. By studying the tiny temperature fluctuations in the CMB, astronomers can learn about the distribution of matter in the early universe, the geometry of space-time, and the processes that led to the formation of the first stars and galaxies. The discovery of the CMB in 1964 provided strong evidence for the Big Bang theory and revolutionized our understanding of the universe's origins. Since then, astronomers have studied the CMB in exquisite detail, using ground-based telescopes, balloons, and space-based observatories to map its temperature and polarization with ever-increasing precision. The CMB is a testament to the power of the Big Bang and the ongoing evolution of the cosmos. It is a reminder that the universe we observe today, with its galaxies, stars, and planets, emerged from a hot, dense state, and that we are all connected to this ancient cosmic event. Our journey through the cosmos has taken us past fiery planets, swirling galaxies, and the echoes of the Big Bang itself. We've witnessed the birth of stars in glowing nebulae, and the death throes of massive stars collapsing into black holes. We've glimpsed the vastness of the universe, a tapestry woven with billions upon billions of galaxies, each a swirling island of stars. But for all we've learned, the universe remains a place of profound mystery. What is the true nature of dark matter and dark energy, the invisible forces that shape the cosmos? Are we alone in the universe, or are there other forms of life out there, perhaps gazing up at their own night skies, asking the same questions we do? These are the questions that drive us forward, that fuel our insatiable curiosity to explore the universe and unravel its secrets. The universe is vast and ancient, but it is also knowable. With each new discovery, with each technological advance, we peel back another layer of the cosmic onion, revealing a universe more awe-inspiring and more mysterious than we could have imagined. Our journey through the cosmos is just beginning, and the future of exploration holds endless possibilities. So, the next time you look up at the night sky, remember that you are looking out at a universe of wonder, a universe that is still unfolding, a universe that we are just beginning to understand. Keep looking up, keep asking questions, and never lose your sense of wonder. The universe is yours to explore.